Hi everyone, I am Mariam from MSc Applied Statistics and welcome to my Iris Species Prediction project. The main purpose of this project is to build a classifier that can predict the species of a new iris flower when we feed it its measurements. We will go through the dataset, analyze it, train a decision tree classifier, and finally see it in action using a simple app. Before we dive in, let's talk about the tools we used. We imported libraries like Pandas and NumPy for data handling, Matplotlib and Seaborn for visualization, and scikit-learn for building and evaluating the decision tree model. We also use joblib to save the trained model and shape for explainability. These libraries are essential to clean the data and train the model and visualize results effectively. To make sure everything runs smoothly, I set up save file path for the dataset, outputs and save model. This ensures the code works consistently whether I run it on my local machine or later share it with others. First, we load our dataset. Here I am using the iris dataset which contains information about different iris flowers. Each flower has features like sepal length, sepal width, petal length and petal width along its species. We check if the file exists and then read it using pandas. If there is an extra column like an ID, we remove it because it's not needed for our analysis. Let's take a quick look at the first few rows. As you can see, each row represents a flower with its measurements and the species it belongs to. These features will help us train our model later on. Next, we explore our data to understand it better. This step is called Exploratory Data Analysis or EDA. Here I am using histogram and boxplot for this. First, we look at how each feature like sepal length, sepal width, petal length and petal width is distributed across different species. I have used histogram for this so we can visually see patterns for each species. Then we check the overall feature distributed using boxplot. Boxplot help us to see the spread of the data and identify any unusual values or patterns. These visualizations give us good understanding of our data before we move on to building our model. After exploring the data, the next step is outlier removal. Outliers are unusual values that can affect the model's performance. We calculate the interquartile range for each feature and remove any rows that have values too far from the normal range. After this, our dataset becomes a bit cleaner. Here we got the output: 146 flowers are remaining, 50 from Iris virginica, 49 from Iris versicolor, 47 from Iris setosa. Here we can also check the distribution of species after removing outliers. As you can see in this bar chart, the classes are still balanced with almost equal number of each species. Finally, we look at the correlation between features using heat map. The heat map shows how strongly each feature is related to the others. This helps us understand the relationship in the data before training our model. Now that our data is clean, it's time to split it into training and testing sets. The training set is used to teach our model while the testing set is used to check how well it performs on new unseen data. Here I have used 80% of the data for training and 20% of the data for testing. I also made sure to keep the species proportion the same in both sets. For the model, a balanced view of all flowers type. This setup ensures that our model will learn properly and can be fairly evaluated later. Next, we want our decision tree to perform its best. So we tune some hyperparameter. Hyperparameters are like the rules or limits we set for the tree, such as how deep it can grow, how it decides splits, and the minimum samples needed at the each node. We use grid search with five-fold cross validation to test different combinations and find the best settings. The model evaluates each combination and picks the one with the highest accuracy. After testing the best hypermeters, we are using the Gini criteria, a maximum depth of 2, a minimum of 1 sample per leaf, and 2 samples for splitting. Then we applied cost complexity pruning, which trim unnecessary branches of the tree to prevent overfitting. The optimal pruning value was found to be 0, meaning our tree is already balanced. Finally, we fit the pruned decision tree on our training data ready for evaluation and predictions. Now that we have a pruned decision tree, let's see how well it performs on unseen data. We predict the species for the test set and compare it with the actual labels. The model achieved an accuracy of 93%, which means it correctly classified most of the flowers. We also look at the classification report, which shows precision, recall, and F1 score for each species. Here, all species have high score, so the model is reliable. To visualize performance, we use confusion matrix. It shows how many predictions were correct for each class. The diagonal represents correct prediction, and our matrix is mostly green on the diagonal, confirming that the tree prediction well for all the species. Now, let's check which features are the most important for our model. To decide the iris species, here we calculate the importance of each feature in the point decision tree. The higher the value, the more influence that feature has on prediction. As you can see in the horizontal bar chart, petal length and petal width are the most important, while the sepal length and sepal width doesn't contribute anything. This tells us which measurements the model trusts the model when classifying our flowers. Next, let's visualize our point decision tree. Here's the tree our model learned after training. Each node split the data based on feature and a threshold. For example, the first split is on petal length. If it's less than or equal to 0.25, the flower is iris setosa. Otherwise, we check petal length. If it's less than or equal to 1.75, it's iris versicolor, and if greater, it's iris virginica. The decision tree clearly shows how the model makes its predictions step by step in a way we can easily understand. Now let's look at the decision boundary of our model. This plot shows how the classifier separates the different species in the feature space. The colored region indicates the predicted class for any combination of petal length and petal width. The points are actual flowers colored by their true species. You can see how well the model learned to separate iris setosa, iris versicolor, and iris virginica. It's like drawing invisible lines in the feature space, and our model is making the right predictions based on these rules. Next, we have the learning curve of our pawn decision tree model. This graph helps us understand how the model accuracy improves as it sees more training data. The blue line represents the training accuracy and the green line shows validation accuracy. The shaded areas indicate variability in scores. Ideally, we want both lines to be high, close, and together, showing that the model is learning well without overfitting. From this plot, we can see that our model is stable and perform reliably even as we increase the amount of the data. Finally, let's talk about shape explainability. Shape helps us understand how each feature contributes to the model's prediction. Using the shape summary plot, we can see which features are most important for deciding the species of an iris flower. For example, petal length and petal width play a major role in classification, while sepal length and sepal width have slightly less influence. This gives us confidence that our model is making decisions for the right reason, not just random guessing. Lastly, we save our train and prune decision tree model so that it can be reused anytime without retraining. This ensures our prediction for new iris flower are fast and consistent. The model is saved as a joblib file, making it easy to load later for any new data we want to classify. And now let's see the classifier in action. Using the simple Streamlit app, you can enter sepal and petal measurement for any iris flower. Click predict and the model will tell you the species along with confidence in level. You can even see the feature important chart to understand which feature influence the prediction. This interface allows you to test the new flower data and see accurate predictions instantly. To sum up, this project demonstrates how decision tree classifier can learn from data and make accurate prediction for new inputs. It's a powerful example of machine learning in action and shows how we can turn data into insights. Thank you for watching and I hope you enjoyed this walkthrough of my iris species prediction project.